Hello, this is the first part of chapter 2.2, and today we're going to talk about inverse matrices. And inverse matrices is a very special type of matrix which is essential to a lot of linear algebra applications. Let's just start by experience the property of inverse matrix, and then we'll bring the proper definition. For example, let's take two matrices, A and C. And let's go ahead and calculate their product, A times C. So this is our matrix A, that's our matrix C, and you probably should be already comfortable multiplying two-dimensional matrix. We take the row, multiply it of the column, get the element 1, 1, get the first row multiply by the second column, get the element 1, 2, and so on so far. And you can perform this algebra. I actually strongly recommend you to recalculate this algebra. And you would notice that the result of the product is an identity matrix. Okay, that's really nice. So let's just do something else. Let's now take the reverse multiplication. We'll multiply matrix C by A. And from the previous chapter, we know that, matrices are not mutable. So the result of the product, if we reverse direction, is not always the same. But okay, let's take our matrix C and multiply by matrix A. And again, we take first column, multiplied first row multiplied by the first column, first row multiplied by the second column, and do all this row columns operation. And surprisingly, we'll come up with exactly the same result. And it's also the identity 2 by 2 matrix. So although we do not guarantee that the product of two matrices when reversed is the same, there is a very special kind of matrices like we see here, when actually it doesn't matter what's the direction of the multiplication, we always get an identity matrix. And those products are, say, called the invertible matrices. And in generally, when we have a m by n matrix, it has to be square. And we say that it's invertible if there is a matrix C such that multiplying our vector A by C will give us an identity matrix. And the order of multiplication doesn't really matter. And we usually call this matrix C an inverse matrix of A, or sometimes we just use notation of inverse, which is the -1 upper script over the given matrix A, just to kind of avoid multiple matrices, because they are, this matrix and its inverse is closely related. This product is always identity matrix. Okay, so how we can actually find an identity matrix? If we are in two-dimensional space, or if we have 2 by 2 matrix, there is a really nice formula which help us to calculate inverse matrix if it exists. So if we have 2 by 2 matrix, we can just denote the element of this matrix A, B, C, and D. And we calculate the very important property of this matrix called the determinant. So you probably heard about it in your pre-calculus class. This is the time to remind. So the determinant is just the product of left diagonal, A and D, minus product of right diagonal, C and B. And the difference between these diagonals is if determinant is equal 0, the invertible matrix does not exist. But if it does not equal 0, then we say that the matrix is invertible, and we can actually find exactly the value for our inverse matrix using this nice formula. So this is the 1 divided by our determinant and multiplied by the matrix, which actually quite similar to our original matrix. We just take our left diagonal and we switch the elements. So the D goes up and A goes down. And from our right diagonal, we keep the element, but we multiply them by -1. And I know it's kind of maybe look a little bit complicated, but if you do it 3-4 times, you almost naturally will remember this formula. But okay, the best way to remember any mathematical formula is applied several times. So let's take the matrix A here, and let's find an inverse matrix, if it exists, using a determinant formula. Okay, so again, just to kind of make everything is order, let's label our numerical values according to theorem 4 notation above. So our 3 here, element 1, 1 will be A. So our B, or element 1, 2 will be 4. Our C, or element 2, 1 will be 5. And our D, which is element 2, 2 will be 6. Okay, so now we have our value for A, B, C, D, so we can use the formula for determinant to figure out if inversible is even exist. Okay, so what's our determinant? Again, according to the formula, we take two left diagonal elements, A and D, and multiply them. In this case, our A is equal 3, our D is equal C, so their product will be 18. So now we subtract the product of the right diagonal element. So our C is equal 5, our B is equal 4, so we subtract their product, which happens to be 20. So when we perform this mathematical operation, we find that our determinant is equal -2, which is a very good news. It is non-zero, which means that matrix A is invertible. Okay, so if invertible matrix exists, let's find it using our nice formula over there. Okay, so what's the invertible of matrix A? Again, we take determinant, which we just found, and put it in denominator. So we have 1 divided by -2. So now we need to multiply it by modify matrix. And again, as we say, we take the left diagonal elements and we switch the order. So our A, which is equal 3, will go to the right corner, and our 6, which is D, will go to the upper corner. And the right diagonal element, we just multiply them by -1. Okay, so now we have matrix which we multiply by a number. So the easiest way to proceed is just distribute 1 over -2 over every single element of this matrix. And then when we just perform the algebra, we can find our inverse matrix. And every time when you find an inverse matrix, the best last step you can take is just multiply inverse by the original and confirm that indeed it will give you the identity matrix. And I left this step for you to calculate. If you cannot find the identity matrix, there is some problems here. Okay, so that's the calculation of invertible in the two-dimensional space, where is the nice formula. Unfortunately, if we go into the higher dimensional space, 3 and above, it's a little bit trickier to find the inversible, so the neat formula does not exist, but there is a couple other approaches which we can take, and we can talk about them in the next part of this chapter recordings.